the slight wobble at the bottom becomes a violent structural deviation. The entire skyscraper of numbers falls on itself. Can the first recognized computer algorithm still run today? The plan was to take the published procedure, run it through a simulator, compare it against a reference. What I did not expect was for Note G to run successfully and still give the wrong answer. The simulation followed the steps, but the result did not match the reference. That meant the real question was no longer, can I make Note G run? It had split into two more useful questions. What exactly does Note G do? And why is it producing the wrong result? That matters because Note G is not just an old mathematical curiosity. It is tied to one of the earliest serious attempts to describe a machine following symbolic instructions, which means this is no longer just a programming exercise. It is computational forensics. Before we can understand why the simulation went wrong, we need to understand what Note G was supposed to do. The short version is this. Ada Lovelace was not just writing down a calculation. She was describing a procedure. A calculation is something a person can do step by step on paper. A procedure says, take this value, put it there, combine it with that value, store the result, reuse it later, then keep going until the job is done. That is where Babbage Analytical Engine enters the room, wearing brass shoes and causing trouble. The Analytical Engine was designed around a few key ideas. It had a store where numbers would be kept. It had a mill where arithmetic would happen. It had operation cards to tell the machine what to do. And it had variable cards to tell the machine which stored values to use. In modern terms, the store is roughly memory. The mill is roughly the processor, and cards are roughly the program. Not exactly, of course, but it's close enough to see the shape of the idea. And that shape is the important part. Note G was an attempt to show that the machine could follow symbolic instructions without a human holding its hand at every step. Values could be stored, moved, combined, reused, and carried forward. That is the idea we are testing. To understand why the simulation spat out rubbish, we have to look at the specific mathematical monster Ada chose to tame: Bernoulli numbers. Think of the Bernoulli sequence not as a static list of figures, but as a towering, precarious house of cards. Every single floor of this tower relies entirely on the structural integrity of the floors beneath it. To calculate the 8th Bernoulli number, you must first calculate the 6th. To get the 6th, you need the 4th. It is a chain of recursive dependency. If your calculation for the base layer is off by even a fraction of a millimeter, the error propagates upwards. It doesn't just stay a tiny error, it accelerates, it compounds. By the time the instructions reach the top of the tower, the slight wobble at the bottom becomes a violent structural deviation. The entire skyscraper of numbers falls on itself. This is what Ada Lovelace was attempting to mechanize. She wasn't just asking Babbage's engine to do basic sums. She was asking a machine made of brass, gears, heavy levers, and punch cards to carry out a multi-story, high-stakes coordination act without dropping a single piece of data. That is why Bernoulli numbers was such an interesting choice for Note G. Such a complex computation is exactly the kind of thing that can expose whether a machine is merely calculating or actually following a procedure. Back to my little experiment. I now had all the pieces on the table: Ada's procedure, Babbage's Analytical Engine, and a mathematical beast that punishes sloppy coordination. The next step was obvious: build a ghost of the Analytical Engine. To test Note G properly, I needed more than a Bernoulli number calculator, so I built a simulator. More honestly, I got AI to help me build one. I chose C++ for this because C++ has a reputation. It is not the friendliest language in the building. The strange part is that I did not have to fight with the syntax. AI handled most of that. Without AI, this simulator would probably have taken me months. With AI, I had a working simulator in a few hours. I'm not pretending the simulator appeared from the mist like some holy artifact of engineering purity. It was built through conversation, prompt by prompt, test by test. For a moment, it looked civilized. which in computing is usually when the trapdoor opens, because the simulator reached the end and the result did not match the reference. The first real test was straightforward. Run the published Note G sequence, then compare it against the reference. If they matched, brilliant. If they did not, the trace would show where things started to drift. The reference gave the expected value for B8, negative 1/30th. Note G did not. That stopped the whole experiment in its tracks. What on earth was going on? So I had to dig into the simulation traces to see what was happening. Oh, what I saw dropped a nuclear bomb on my head. After digging through the traces, I found references to a possible bug in the fourth operation of Lady Lovelace's algorithm. Even the Wikipedia entry for Note G mentions it. But I did not just want to repeat the claim like a man confidently reading road signs from the passenger seat. I wanted to test it. Now, for the curious, Operation 4 tells the machine to divide the value stored in V5 by the value stored in V4, then places the result in V11. In plain terms, V5 divided by V4. The suggested repair is to reverse it, V4 divided by V5. It's a tiny change, one division facing the wrong way. But in a symbolic procedure, tiny mistakes have ambitions. The result from Operation 4 feeds into the next part of the machine state. Then that state gets reused. Then it affects later operations. This is not just one bad calculation sitting quietly in a corner. And once bad state enters the system, the rest of the procedure can behave perfectly and still produce nonsense. So I asked AI to help create a corrected version of Note G and run it side by side with the original and the reference. By the way, if you want the code for the simulator, the repository is linked in the description below. So I ran the comparison. And ladies and gentlemen, Lady Lovelace's famous Note G has a bug indeed. The first documented complete computer program is defective. Some people get fired for writing bad code, but Lady Lovelace here gets to be a celebrity. I thought that was the end of it, but then the repaired version of Lady Lovelace's algorithm produced a new problem. The numbers were now behaving. The sign wasn't. It turns out Operation 4 was not the only wound. There was another one. Instead of landing on negative 1/30th, the repaired version was pointing at positive 1/30th. A minus sign is not a tiny horizontal garnish. It changes the entire meaning of the result. So now I had a second problem. Operation 4 fixed the direction of the division, but it did not fix the symbolic polarity of the final answer. In plain English, we had patched the wound, but the patient was still bleeding from somewhere else. So I went back into the trace. Fortunately, I didn't have to write a single line of code. I asked AI to figure out why there was still a mismatch in the corrected version of Lady Lovelace's algorithm. It didn't take long for the robot to point at the problem. Line 24. This is where the procedure combines one of the intermediate values with the running result. In Note G, the operation behaves as though the value is being added in the wrong direction. AI suggested reversing the movement. Instead of pushing the result toward positive 1/30th, it needs to pull it back toward negative 1/30th. I typed out a prompt, asked AI to fix the problem, and went off to make tea like a man contributing absolutely nothing to science. Don't you just love coding in 2026? When I came back, the problem had been fixed. The corrected symbolic chain landed where the reference said it should, negative 1/30th. So there it was. Not one issue. Two. The fourth operation in Lady Lovelace's algorithm sent the machine down the wrong computational road. Line 24 gave the results the wrong symbolic sign. Two bugs. Lady Lovelace was in trouble. I was about to take my findings to the High Court of Reddit so that this fraud, Lady Lovelace, would finally be exposed. But there was also a more serious point hiding underneath. The machine was doing exactly what symbolic machines do. It was following instructions. It didn't know which instruction was historically meaningful. It didn't know which sign was mathematically sensible. It just obeyed the procedure. And when the procedure was wrong, the machine preserved the wrongness with religious discipline. That is the lesson. A symbolic machine can be powerful, elegant, and completely obedient, but obedience is not understanding. So yes, I'd found the second wound, and with both repairs applied, the result finally matched the reference. For the first time in this investigation, Note G passed the test, which should have been the end of the story. Unfortunately, it was not. For a few glorious minutes, everything looked good. The fourth operation in Lady Lovelace's algorithm had been corrected. I also fixed line 24. Well, AI did. The repaired Note G simulation was working finally. Negative 1/30th. At this point, I wanted to declare victory, close the laptop, and begin writing my Nobel Prize speech. But that would have been too easy, because passing one worked example is not the same thing as surviving the wider problem. Ada's original Note G was aimed at a specific target. It was not a general-purpose Bernoulli number engine, where you simply type in any value of n and let the machine gallop off into algebraic misery. So because I had nothing better to do with my weekend, I decided to torture my brain cells further. I wanted to find out if Note G could be modified to calculate larger numbers in the Bernoulli sequence. I knew this was going to be demanding on the machine's resources. I had a hunch that pursuing this little experiment would help us understand whether Babbage Analytical Engine was even possible to build, given the technology of that time. That meant asking what happens when the machine has to carry more previous values, more intermediate results, more signs, more fractions, and more opportunities to drop something important into the swamp. Essentially, I wanted to find the machine's breaking point. And that meant pushing the simulator beyond Ada's worked example. This is where the story stopped being about whether one table had two defects. It became a question of scale. How much symbolic pressure can the machine survive before something breaks? Once the repaired simulation worked for Ada's example, I wanted to see what happened when the problem grew. This is where the experiment became more interesting, because the difficulty was not just finding the final number. It was everything the machine had to keep alive on the way there. The store gets busier, the mill does more work, the instruction count grows, the fractions become uglier. The numerator and the denominator start swelling like they've found government funding. At this point, I needed more than correct output. I needed measurements, so I started tracking resource usage. How many times does simulator read from storage? How many times does it write back? How many arithmetic operations does the mill perform? How many instructions are executed? How much working state has to be kept alive? How large do rational numbers become before the final answer appears? Condensed into one question, how much symbolic baggage does the machine have to drag behind it while calculating this? And the answer was a lot. As the Bernoulli index increased, the computation became heavier. The dependency chain grew. The intermediate values became more awkward. The rational numbers widened. Everything started to feel less like a neat Victorian table and more like trying to organize a wedding where all the guests arrive as fractions. This is where the analytical engine question became more serious. Because if my simulator was already showing pressure, what would that mean for a mechanical machine made of columns, cards, gears, and heroic amounts of patience? Could Babbage's machine have coordinated all of this? Could it store the values, move them correctly, preserve the signs, reuse intermediate results, keep the sequence under control? Because the deeper challenge was no longer just arithmetic. It was sustained symbolic coordination. And the further I pushed the simulator, the more obvious that became. The procedure did not merely grow, it crowded the machine. The ghost was starting to sweat, and then I pushed it far enough to hit the first real wall. The first real wall appeared at the 36th number of the Bernoulli sequence. Now I apologize for this next section if you're not conversant in C++. The expected Bernoulli value contains a numerator large enough to make 64-bit integers start sweating through their shirt. The numerator is, I'm not going to bother reading that. Now, In C++, variables of type long, also known as 64-bit integers, only allow a maximum of, But if you compare the two, you will see that the first number has more digits. It does not fit. That is where my first simulator hit the boundary, because the number had outgrown the box I had given it. The symbolic idea was still alive, the machine representation was not. I thought of ditching the 64-bit integers and using doubles instead. And yes, doubles have a much larger range. They can hold enormous values, but there is a catch. Doubles do not preserve exact rational values. They approximate. They can give you a very convincing shadow of the number, but not always the number itself. And Bernoulli numbers are the kind of creatures you want to handle with precision. Even 1/6, which appears early in the sequence, cannot be represented exactly in binary floating point, also known as double. So using doubles dodges the overflow dragon and walks straight into a rounding problem. That's a different monster, but the same bad neighborhood. The better solution was to use arbitrary precision integers. In C++, these are variables of type cpp_int. They are found in the Boost library, for those who care. This variable type allows the numerator and denominator to grow as large as memory allows. That moves the wall further, but it does not remove the deeper lesson. Every machine has a numeric model. Every numeric model has limits. And when symbolic mathematics gets large enough, those limits stop being theoretical and start kicking the furniture. That is what this little incident taught me. The computation did not merely need instructions. It needed a representation strong enough to carry the numbers. And the moment the representation failed, the whole experiment changed again. Because now I was no longer just asking, can the procedure be repaired? I was asking, what kind of machine can actually survive this? At this point, the question became much bigger than my C++ simulator. Because if a modern program could run into trouble just by choosing the wrong numeric representation, what would this have meant for Babbage's Analytical Engine? Remember, the Analytical Engine was not going to run on silicon. It was not going to have RAM. It was not going to have a debugger. It was not going to have a terminal politely showing where the numbers had gone wrong. It was going to be mechanical, with columns, cards, gears, decimal digits, physical movement, the sort of machine where state management means actual pieces of metal remembering what just happened. That is both beautiful and terrifying. Because Note G does not only require arithmetic, it requires coordination. The machine has to fetch the right values, send them to the mill, perform the right operation, store the result, reuse it later, preserve the sign, preserve the fraction, then do the next operation without dropping the entire symbolic operation on the floor. And the more I looked at the simulator traces, the more respect I had for the ambition behind the analytical engine. This was not just a big calculator. That description is almost insulting. A calculator gives you answers. The analytical engine was supposed to manage procedure. It was supposed to follow a sequence of symbolic instructions without a human manually steering every step. Yes, I found defects in Lady Lovelace's algorithm. Wonderful. Give me a fucking biscuit. But I found them using AI, a high-level programming language, terminal traces, and the ability to run the same experiment over and over until the machine confessed. Lady Lovelace did not have that. She did not have a compiler. She did not have a working analytical engine. She did not have VS Code sitting there with colored brackets like a tiny judgmental Christmas tree. She had paper and Babbage's unfinished machine, and the task of imagining how symbolic procedure could work on hardware that did not yet exist. That is a ridiculous cognitive load. Besides, we do not know yet whether Ada introduced the defects herself, or maybe it was the engraver or transcriber who introduced them. Maybe it was a publication. Maybe later reproductions of this document introduced these errors. So yes, I had my fun. Lady Lovelace was briefly dragged through the mud. But the more honest conclusion is this: I was not standing above her work. I was standing on top of almost 2 centuries of tools that made my little experiment possible. That changes the tone, because the defects are interesting, but the achievement is still enormous. Ada saw that Babbage's machine was not limited to arithmetic in the ordinary sense. She understood that if symbols could be represented and rules could be applied, then the machine's potential went far beyond number crunching. The machine could manipulate symbols according to rules, and if it could do that with numbers, perhaps it could one day do it with other symbolic systems too. That is why Note G matters, even with the wounds. Maybe especially with the wounds, because the wounds show how fragile symbolic procedure can be. And the vision shows why it was worth attempting anyway. So, could the analytical engine have survived this? Probably not. The coordination burden would have been brutal. The engineering tolerances would have been very unforgiving. Debugging code would have been a Victorian punishment ritual. But conceptually, the idea was there. The shape of modern computation was already visible. A machine, a store, an arithmetic unit, instructions, state, procedure, failure, repair. And that is the strange beauty of this project. The bugs did not make Note G less important. It made the difficulty visible. It showed that symbolic computation is not magic. It is coordination under pressure. And pressure is exactly where machines reveal what they really are. If you've made it this far into the video, congratulations, you're a nerd. And I mean that with deep respect. I've got a little treat for you. The code for the simulator is available if you wish to scrutinize it. Check the link in the description below. I've also put together a detailed breakdown of how I conducted these experiments over on my website, including the research notes, simulator approach, and the results. That link is also in the description. If you enjoyed this kind of thing, you should check out the next video where I tried to cram Lady Lovelace's algorithm into an HP11C calculator. Yes, that is what I do with my weekends.